Thank you very much. I'm a little embarrassed to say that the number of times I start a talk by saying, and now for something completely different, it happens quite a bit. And now for something completely different. I'm an electrical engineer. Typically when I give presentations like this, I'm depressed because the kind of electrical engineering I do does not admit beautiful pictures. And then after Tom's talk this morning, I realized that not only do I not have pretty pictures, I don't have devices or projects to bring with me. So just to give you some context, so I received my PhD in 1994, and this was the big thing. All right, we were all worried about how to design wireless communication systems. At that time, it was still cool to do point-to-point communication, one transmitter, one receiver. That's no longer cool. And so here we are now. Things have changed dramatically. So one of the questions we can ask ourselves as an electrical engineer, a communications engineer no less, is why should we study these biological systems? I know that I'm preaching to the converted, but the reason for my putting this slide up is to provide a little bit of context in terms of the perspective that I take when I talk about these. So there are two different applications, if you will, that we're very interested in. One of them is more from the perspective of trying to understand how actual real biological systems work. I am not a biologist, I am not a microbiologist, but I work very closely with those kinds of individuals, and my hope is that they will keep us honest in terms of the modeling work that we do. From a more pie-in-the-sky perspective, just like Max, thank you, Max. Thank you, Ivan, for the invitation. Very happy to be here. We're also very interested in molecular communication systems. And so the notion of can we design systems that can work in this kind of environment using molecular diffusion as our medium for transferring information. So two very different ends of these kinds of problems. And so in particular, the questions I'm interested in is, and I hope I don't offend any more biologists than I have already, but we really want to know how much we can abstract. How much can we simplify the models? Because, of course, life and biology is complex. Certainly, the systems that we're looking at have been modeled by very capable individuals before. The difference is that we are trying to simplify things as much as possible to see if we can ask and answer engineering types of questions, which is, can we optimize? Can we design? Can we control? And so this is an important question to us. How much of an abstraction can we do such that our resulting models are tractable but are still informative about the biological system that we're trying to understand? And then a question which I think the answer is in the affirmative, but let's keep it speculative for the moment, which is, do we gain anything from taking these engineering perspectives from disciplines like communication theory, information theory, control theory, and signal processing, and do we get anything out of it by looking at these problems through this lens? And I have to be very frank with you, I am an engineer, so this is the lens that I employ in order to look at these kinds of systems. And perhaps very importantly, we are actually very interested in operational behavior. And so do these analyses tell us a little bit about how these systems behave in a way that is understandable to us engineers with perhaps the smaller brains than the biologists. So let me take you down this path. I'm blessed to have an amazing set of colleagues in the biological sciences at USC, and so I've been interacting with a number of them. Ken Nielsen is actually the person who got me down this path, who I think of as kind of one of the grandfathers of quorum sensing. But he introduced me to Mo El-Najjar and Steve Finkel, and they were very interested in this problem of bacteria forming these filaments or cables. And as I understand it, these kinds of systems exist in the wild, and people are still unclear as to why they happen. And one of the reasons why they're surprising is because the amount of nutrients at the bottom of the cable and the top is very different. So why don't the bacteria just all merge to where the food is instead of forming this kind of system where, in addition to holding hands, if you will, they also create this sheath which facilitates electron transport between the bacterium. So why does this happen? Now, if you were me, and maybe a couple of other people in the room, when you see this, this is actually what you see. So in wireless communications, people have been thinking about multi-hopped communication for quite some time. In fact, Charlie DeSora, with whom I had the honor of taking a few controls classes when I was a graduate student, master's student at Berkeley, his PhD is all about multi-hop networks. and a lot of his results presage some things that we are very familiar with now in information theory. So folks have been looking at these multi-hop systems from a communication and information perspective for quite some time. And so, you know, I've studied this. So my first reaction was, this is a multi-hop network. I know something about multi-hop networks. Can we endeavor to take my strategies to try to understand what's going on in this particular problem? But of course, the moment you say, I know multi-hop networks, and you're thinking about biological systems, you're invoking a lot of hubris. So let's be clear that obviously there's only so much we can say. So this picture here is the result of a tremendous amount of arm wrestling between the microbiologists and the communications engineers. Again, it comes down to how can we abstract things? What are you going to allow me to throw away so that I can come up with a model that's tractable? And again, in biological systems, people have modeled things very accurately. People know about diffusion. You know how to describe them. There are massive amounts of differential equations. They're interconnected. They're complicated. There's a form of complex numerical analysis that goes on in order to see how these kinds of systems work. And again, my objective was try to do some kind of optimization. So for this particular system, where we were trying to understand electron transport between bacterium, we were able to reduce ourselves to 4 different queues. Aurel is very familiar with this kind of modeling strategy because it's used a lot in networking. And you may not know this, you may not know him as a neuroscientist, but some of us remember when he was a communications network engineer and did a lot of amazing work in that arena. And so we're considering the various quanta in the system to be populating these queues. I have molecules from the outside that diffuse in. They in turn feed into a queue where it creates electrons here. I also have electrons coming from my previous bacterium going to my next one, et cetera. And so there is a series of equations that describe this. What's hidden are biological constraints, but this is something that we took into consideration. Our hope had been, with our earlier interaction with our microbiologists, and because we had developed this model with the microbiologists, that they would have data sets that would allow us to validate this particular model. I have now learned that you only design problems for which the data has already been taken, and that it's not going to be taken. So simultaneous measurement of ATP and NADH in the particular bacterial strains that my colleagues were studying apparently is quite challenging. I've been promised the least important author position in the Nature paper if they ever get this measurement down. So what we did do is take data from the literature where we looked at a single cell, and what you see is that our predictions of how ATP would evolve as a function of time, given a bolus of glucose being added at this time, match very carefully and very closely. And so, very simplified model. A lot of signal processing had to happen in order to create the calibration for the data to make things match up. And I want to emphasize that our stochastic queuing model is much more simple than the detailed underlying physics. But from our interactions with our colleagues, we believe that it is capturing the salient features of the model. We've also parlayed this into trying to assess the maximum amount of electrons that can be transferred in one of these cables. This is a very simplified model. There are a long list of approximations that had to happen in order to make this. And despite this series of approximations, the information theoretical results are actually quite nice. And they generalize things that Toby Berger had done, also motivated by biological systems. So if anyone wants to know the details on that, I would be happy to share it. So sort of emboldened by that, we decided to see if we could look at bigger problems, more complicated networks, if you will. And I'm very grateful to Professor Collins's presentation, where she gave a much more detailed description of what happens in quorum sensing. But to provide a little bit of context, at the time that we were thinking about these problems, this was sort of the modeling that was going on in my community, all right, communications engineers, where people were just focusing on whether molecules will bind or not. It was a simple 2-state Markov system, and we were looking at the capacity of that kind of system. And again, in discussions with our microbiology colleagues, we realized that for them, this model was too simple. So once again, the arm wrestling ensued, and we came up with a different kind of model, which again, following with the success that we had before, we used this stochastic queuing framework in order to capture the various quanta in the system. What's hidden in here is that the construction or creation of synthases, complexes, et cetera, are all governed by probabilistic behaviors. And so there's a whole series of different probabilities of whether different events are going to occur. Now, one of the nice theoretical results of this is that when we started doing this work, we thought we were going to have to keep track of all of these cues in every single bacterium in our simulation or our system. And so there's a nice technical result that says you don't need to keep track of all of them. Given the assumptions that we have, you actually only need to keep track of aggregates. And so this makes simulation much simpler to do. This is, again, a validation with experimental data, this time from James Bodeker's lab, where they were looking at E. coli. And we were able to, again, to get a very good fit. Now, one of the things that was missing from this particular modeling approach is that, so as Cynthia explained, one of the things that occurs in quorum sensing is that there's this compound that's created, or extruded, if you will. The bacterium have the ability to sense the presence of this compound in the environment, and the conventional wisdom is, and we have no reason to debate that conventional wisdom, is that each bacterium can decide whether the amount of the compound in the environment has exceeded a threshold or not. If it exceeds a threshold, then it is worthwhile for the bacterium to express new genes, produce an enzyme, whatever it is. This decision-making of the individual bacteria is hidden in what we've done. It has not been made explicit. It is present there. And so the next thing that we wanted to do, which was not turn things off, there we go, sorry, hit the wrong button, was to change our framework and look at things from the following perspective, which is let's treat each bacterium as if it was an individual decision maker that was making noisy observations and deciding whether it should activate or not, whether it should express a gene or not. And in this regard, we're essentially modeling this microbial population as if it was a sensor network in a wireless environment. Again, a framework that we are used to studying in prior work that we have done. So how does this work? I debated whether I should include an equation or not. You don't need to parse this. Let me just simply emphasize one key point, which is that there's an objective function that we want to maximize. It's a function of what's going on in the environment, the population, and some decision making. What's important here for what I want to share is this notion of how do we discount what happens in the past? Do I assume that the past has no impact on the decision making that I'm going to do? In which case, if I have a zero discount factor, I'm looking at instantaneous costs and gains. But if I have a non-zero discount factor, we realize that, again, the control theoretic interpretation of what we have is that I want to invest some of my population today in order to have a greater population in the future. And so a question is whether bacteria actually do this. Are they thinking ahead? Are they looking ahead? And so an interesting theoretical result is that in the noiseless case, we can actually prove that the optimal decision-making function for each bacterium is a threshold, which is exactly what our microbiology colleagues believe to be true. But what we don't know, in fact, and we're trying to assess this now, is whether every bacterium actually has its own threshold. And now this notion of single-cell variability seems to be very popular, at least amongst our microbiology colleagues, which now gives us permission, if you will, to employ some of these statistical models that we like to do. So this is semi-hot off the presses data. So what I'm showing you here is the noisy case. We have three different cases here. In the blue case, the bacterium are always off. They don't activate. In the purple, they always do. And the red, they are sensing the environment and deciding whether they should activate or not. And so these are, of course, the computed curves based on our control theoretic view of this problem. What you see on the right is the data from synthetically engineered E. coli. And you see that the trends that were predicted by our analysis are exactly matched by the data here that you see. The reason why these things don't look even more beautiful is because we haven't done the parameter calibration yet, and then we will have a much tighter fit. So I have a feeling I was... So again, bacterium always off, never activating. It still has population growth. Bacteria always on and producing this expensive enzyme, so they do have growth. I'm sorry, this is the red curve here. And the purple one, they're engaging in quorum sensing. So you're getting the best of all possible worlds. You're not doing expensive activities when they don't benefit you, and you're engaging in expensive activities when they do benefit you. OK, So I probably won't be able to cover the molecular communications work as much as I want, but here this is a more classical problem for me as a communications engineer, because we're essentially trying to design communication systems that use molecular diffusion as their modality. And we've investigated this from a lot of different perspectives. So let me just jump to one set of results, and then I will end. One of the things that we engineers often do, which I'm sure the biologists hate, is that we assume that things can be synchronized, that we have perfect timing at transmitters and receivers, which of course we can achieve in this, but we cannot assume to be true in biological systems. So we wanted to understand what the impact was of having synchronization errors at receivers, and could we design them in order to do this? And the short answer is, without going through the curves, is that yes, you can actually introduce a lot of robustness into these receiver systems in a very simple way, and it's not hard to do. And on top of it, we can come up with a theoretical explanation as to why our particular strategy works well for this communication environment. So let me stop here with a few things. So obviously there's significant opportunities. One plea that I make to my biology comrades that are out there is that we as engineers, unless we have excellent collaborators, do not have access to good data sets. All right? Well-curated data sets where there's information about how the data was constructed. And so one of the things that I did as the outgoing editor-in-chief of a new communications journal on this type of topic is to create what are called methods papers, again being informed by science and nature. And the idea was that you would describe your experimental methodology, you would have a data set that would be publicly available. Perhaps there's also pre-processing code that people can use. And the hope is that we democratize things, and so that individuals who don't have access to excellent collaborators like all of you in the room still have the ability to participate. And what's in it for you? Well, the hope is that if you are using this data set, then you have to cite the paper. So, you know, I'm trying to help with the whole weapons of mass destruction H-index battle here, all right? We've also been creating data set competitions within my community, which are not normal, in order to encourage people to think about playing with these data sets. I realize there's one last thing that I forgot to do, and so forgive me. I wanted to put out a shameless plug. The postdoc who's been doing this amazing work that's made these two things connect to each other is Marcos Vasconcelos. He's in the back of the room. He had a poster, and he's on the market. Thank you very much.
Is setting up. We can have time for a question.
Yes, Max.
Okay, thank you for representing my community. And I just want to ask you, what is your vision to translate all these models and ideas into engineering something?
Yeah, so you ask a very good question. I have been starting discussions. So we have a lot of people that do microfluidics at USC, and I've been trying to start some of these discussions as an arena to see what we can do, but let's just say translation takes a little bit of time, and I'm very grateful to be officially an old full professor who can take the time to have these conversations. But I'm optimistic, actually, just because there is a lot of resident expertise at my institution in this kind of thing. Now, again, another shameless plug. As you probably know, Nariman Farsad, again, electrical engineer on our side, has systems that you can buy that do in-the-air molecular diffusion. And if you wanted to do your own tabletop experiments, you can. My only concern about a system like that is that it's far from the reality that I'm particularly interested in, where the medium tends to be fluid and the molecules that we're talking about are much smaller. So, I mean, I think edge effects and scaling matter tremendously. So I hope, especially for those of you who have these cool semi-syn bio grants, create test beds that the rest of us can borrow and emulate. The challenge is out there. Thank you.
Thank you. Let's thank the speaker again.